Circuit essentials. I'm going to see how fast and effectively I can fit these concepts into your puny brains with thunder and rain in the background. Just ignore that. Voltage and current. People probably think they have a good handle on what that is, but in my experience, I need to explain the difference and give some examples. We'll go into op-amps, operational amplifiers, their importance, how they operate. They're very critical for all types of circuit operations. Using op-amp circuits as building blocks for more complicated circuits. Linearity is an important concept that comes into play very heavily. I'll go over that, and then I'll do some circuits combined using linearity and op-amp circuit building blocks. So first of all, you have to understand, how can you have voltage without a current? And how can you have current without a voltage? Understanding these two things helps to understand voltage and current, the difference between the two. And in particular, having a voltage without a current comes into play significantly in op-amp functionality. So having a voltage without a current. Here's one example. A battery. It's got a voltage difference between the two terminals. There's no current unless you consider the fluctuational currents inside, but those we can ignore. Okay, so how about a non-zero voltage and current? That's the typical thing that you would expect to be working with. We have a battery that is holding a constant 1.5 volts. And whenever we consider a battery here, it will always be an ideal battery that holds 1.5 volts. There'll be one exception. It'll come up. The current always goes in the opposite direction of the electrons, thanks to Benjamin Franklin. So, what determines the voltage across the resistor? We have a current coming out of the battery. Does that current determine the voltage? You might think, if we change the resistance, what are we changing? Are we changing both V and I? V equals IR? Well, VR is always the same in this case because it's parallel with the battery. So what determines I? Well, if VR is constant and the resistor follows Ohm's law, it's I times R, then I depends on R. Now, power, if you have a dissipative element like a resistor, then it's convention to say that power is positive. It's being dissipated into the resistor. Then there must be power coming from somewhere to be dissipating, so that power is coming from the battery. That's a negative power. So power computation does not involve Ohm's law, or it doesn't have to. As you can see here, the power being provided by the battery is I times V, and there's no Ohm's law involved in that. Ohm's law for the resistor, the power being dissipated in the resistor, you will use Ohm's law to calculate that. And that's necessary in order to know how much power is being delivered by the battery, or you could just measure the voltage across the battery and the current coming out of it, and you would know that that much power being delivered must be dissipated in the circuit. So now if you add a resistor, you have multiple resistors, then you have a variable voltage. You have voltages that change and current that changes with those voltages. And the way that these are all variable is through the resistances. So no longer do we have just a constant voltage across each of these resistors. The relative voltage across each one depends on the relative size of these resistors. The total voltage across, so the voltage from here to here is always constant. That's the same, because that's determined by the battery. So however much energy is increased when you go across the battery, so there's a potential increase across the battery, that same amount of potential must be dropped. And that's the essence of Kirchhoff's voltage law, KVL. It's just kind of the same idea as if you're going on a hike on a mountain and you start at one spot on your hike and you go all the way up and down, let's just say all the way up to the peak, and then go down a different path. Even if you go down a different path, if you end up at the same spot you started, then your potential energy change is zero. So that's the essence of KVL, is that you can sum up all the potential across each element and the sum will be zero. But still, that doesn't say anything about how to find the voltage across each of these. To do that, there's a voltage divider. Let's say we wanted to find VR1 equals, using Ohm's law, it's IR1, but we don't know what I is yet. We know it's there. By the way, the polarities I've chosen here are somewhat arbitrary. They are completely arbitrary, but I've chosen them because I already know I'm at the highest potential here, which means I know I'm dropping potential from here to here. I'm dropping potential from here to here. But in a more complicated circuit, you just have to choose your polarities and choose the direction of your currents. Choose what you're going to label them as. In other words, just choose the labels. You're not actually choosing the voltages and currents, you're choosing the labels. And then once you plug in all the numbers, the signs will work themselves out, as long as you haven't made a mistake somewhere. So back to VR1 equals IR1. How do we find VR1? Well, we have to know I. And what we do know about this circuit is that I goes through both resistors. So if we knew the voltage drop across both resistors, we could use Ohm's law across both at the same time. So I equals the voltage across both resistors, which is the voltage being put out by the battery, divided by the total resistance that voltage is being dissipated across. So then if I plug I in up here, I have V bat over R1 plus R2, and then we still have the R1. So this equation here is called the voltage divider. And notice it's called a divider because we're dividing down the battery or the source voltage. This is being divided by this ratio. So just remember, it's always the voltage across whichever resistor you're trying to find is the current through the resistor times the resistor. And so this resistor here is always on top. So I gave you a hint that the battery voltage isn't always constant, and this is the one obvious exception. Even under ideal circumstances. So if we're talking about ideal batteries, in this case, even the ideal battery, it can't hold its designed voltage because it's shorted. It's got a clear, unobstructed path from the high potential side to the low potential side across a perfect conductor. So it's shorting across the resistor, the voltage is 0, and the battery is going to burn out. There's going to be infinite current, essentially, being pulled out of the battery, and it's going to get hot. So if you've ever connected the terminals of a 9-volt battery, you'll notice that after a few minutes it'll get hot, and it causes fires, or can cause fires. So we talked about the voltage without a current. We've talked about non-zero voltage and current. And now we have a zero voltage with a non-zero current. How is that possible? Stop and think about it. Now I'm going to tell you. So I have non-zero voltage drop across the battery. I have a non-zero voltage across here. Where do I have 0 volts? Well, I'm dropping 0 volts everywhere along the wire. So if I take any location, V wire, from that location to that location, I have 0 volts, but I have a non-zero current. I can do this game anywhere along this wire. So that's how I can have a current without a voltage. Okay, so we've gone over voltage without a current, current without a voltage, non-zero both, and 0 both.